In this video, we're going to take a look at Rolle's theorem. And let's see what Rolle's theorem means by just looking at a picture. So let's suppose we have a closed interval here, where we have a continuous function on this closed interval. And moreover, let's suppose that f of a, if this is a, and this is b, let's suppose f of a is equal to f of b. What Rolle's theorem says is that we're guaranteed to have some values in between a and b where the derivative is 0. And by looking at this picture, we can probably believe that. So let's go ahead and write out Rolle's theorem in a formalized way. Suppose y equal to f of x is continuous on the closed interval a to b, and differentiable at every point in the interior of this closed interval, then if f of a is equal to f of b, then there is at least one point C in the open interval a to b where f prime of c is equal to 0. So where the derivative is 0. Right? And again, this is exactly what we had discussed when we looked at the picture. So we're going to do an example here. So example 1 says that we want to verify the hypotheses for Rolle's theorem are satisfied by f of x equal to x cubed minus 2x squared minus 4x plus 2 on the interval -2 to +2 on this closed interval. Then, after we do that verification, find all numbers C that satisfy the conclusion. Okay. So, how do we do this? Well, the first thing is we want to verify the hypotheses for Rolle's theorem. So to do that, first, what are the hypotheses? There's really three. The first one is that our function f of x is continuous on this closed interval. The second one is that the function is differentiable on the interior of that interval. And the third hypothesis is that f of a is equal to f of b. So when we plug in the endpoints into our function, those are equal. In other words, we have a horizontal secant line between those 2 points on our graph. If all three of those things occur, then we know there exists at least one place on the interior where the derivative is 0. So, how do we verify that our hypotheses are satisfied here? Well, first, this is a polynomial, which we know is continuous everywhere. We also know it's differentiable everywhere. So our first two hypotheses are satisfied. So first two hypotheses are satisfied since f of x is a polynomial, thus continuous and differentiable everywhere. So certainly it is continuous on the closed interval and differentiable on the open interval. Okay, well, the last hypothesis here is that f of a is equal to f of b. So that means we need to find out what f of negative 2 is. Well, just plug that in. Negative 2 cubed minus 2 times negative 2 squared minus 4 times negative 2 plus 2. This is negative 8 minus another 8 plus 8 plus 2 gives us negative 6. Okay, well, what is f of positive 2? This is 2 cubed minus 2 times 2 squared and minus 4 times 2 plus 2. Well, this is 8 minus 8 minus 8 plus 2. Those cancel. We get negative 8 plus 2 is negative 6. So, in fact, f of negative 2 does equal f of positive 2. So, we are good there. All right, so that's the first part of the question. And the second part of the question is then to find all numbers c that satisfy this conclusion. In other words, find all points c between negative 2 and positive 2 where the derivative is 0. So what is f of x? F of x was, again, the function x cubed minus 2x squared minus 4x plus 2. So f prime of x is equal to 3x squared minus 4x minus 4. Okay. And then we need to find all points where this is 0. All right, so you can attempt to factor this, or we can plug this into the quadratic formula, so which is negative b plus or minus the square root of b squared minus 4ac all over 2a. So if we go ahead and plug all of this in, we get positive 4 plus or minus the square root of negative 4 squared minus 4 times a times c all over 2 times a. All right, well, what does that equal? This is 4 plus or minus the square root of, let's see, we have 16 minus negative 48 all over 6. So this is equal to 4 plus or minus 16 minus negative 48 is 64. So the square root of that is 8 all over 6. So we get 4 plus 8 over 6 is 2. And we get 4 minus 8 is negative 4 over 6 is negative 2/3. All right, so there is all of our points where the derivative is 0. But positive 2 was one of the endpoints. So really all we care about is this value right here, the negative 2/3, because that's the only one that's actually inside our interval from negative 2 to positive 2. And that concludes our first example in this video. Now we're going to see the power of Rolle's theorem. We just practiced it in this previous example, but in this upcoming example, we're going to see what kind of problems it can help us solve. So we're going to show that the equation x cubed plus 3x plus 1 equal to 0 has exactly one real solution. First, how do we show that there is at least a solution? Well, to show that there is at least a solution, we can use the intermediate value theorem to show at least one solution. So first, to use the intermediate value theorem, you must have that f of x equal to x cubed plus 3x plus 1 is continuous on the interval, well, it's continuous everywhere, but in particular, it's continuous on the interval -2 to +1. Now, why did I choose this interval? If we recall, for the intermediate value theorem, we need one value to be less than 0. Why 0? Because by one value, we mean when we plug this into our function, we need f of a to be less than 0. And why do we know 0? Well, it's because that's what this function is equal to here. That's what we're trying to solve. And we need f of b to be the opposite, either equal or greater than 0, depending on whatever f of a was. It needs to be the opposite of that. So what is f of -2 here? We get -2 cubed plus 3 times -2 plus 1. So -2 cubed is -8 minus 6 plus 1, and certainly that is less than 0. What is f of 1? Well, that is 1 cubed plus 3 times 1 plus 1, which is certainly greater than 0. So, if our function is continuous, and on one side here of this interval the function is less than 0, on the other side it is greater than 0, then certainly it crosses 0 by the intermediate value theorem, and thus there is at least one real solution. So we had to use the intermediate value theorem from several sections ago to tell us that there is a solution. Now, with the information we gained in this section, we can now say that there is exactly one real solution, as in there is no other solution. Now, how do we know that? Well, let's suppose that there was another solution. If there was another solution, then Rolle's theorem would say that there is some point in between this solution and the we found here. We didn't really find what it was, but we know it exists. So there would be a point between the solution we know exists and this other hypothetical solution where the derivative is 0. Well, why? Well, if we had one point where we plugged it in, we get 0 here. And then we have this other hypothetical point where we plug it in, we get 0. That means f of a and f of b, for whatever those 2 points a and b are, would equal each other. This function is certainly continuous on that interval and differentiable on that interval. So Rolle's theorem tells us that the derivative at some point in that interval is 0. Again, that's if we had this second hypothetical solution. But here's our issue with that. If we take the derivative of this function, we get 3x squared plus 3. This function right here is never 0. So we could never have a point where the derivative is 0. That right there tells us that we must have made a wrong assumption when we assumed there was a second real solution to this function. So there is only one real solution. We didn't find the solution. That's okay. We weren't asked to. We were asked to only show that there exists a solution, and in fact there is only one solution. Okay. I actually still have one last thing I want to do in this video, and that is to prove Rolle's theorem. Well, we can break this up into 3 cases. Case 1, what if our function is a constant? Well, if our function is a constant, then the derivative is 0 everywhere, and certainly the conclusion of Rolle's theorem is thus true. Case 2 is what if f of x is greater than f of a for some x in the interval a to b? Well, by the extreme value theorem, f must have a max somewhere in the closed interval a to b, but since f of x is greater than f of a and f of a is equal to f of b, then the maximum is inside the open interval a to b. And so f of x has a local max at x equals c in this open interval. Well, if we have a local maximum, that tells us that f prime of c must equal 0 there. And how do we know that? Well, again, we're assuming the hypotheses of Rolle's theorem so that our function is continuous on the closed interval. It's also differentiable at every point on the interior. So we know the derivative exists, and we have a local maximum. And by a previous theorem, this tells us that our derivative must be 0 there, which is the conclusion we wanted of Rolle's theorem. And the only other possible case is that f of x is less than f of a for some x in the interval a to b. And here, I'm not going to rewrite the proof, but the proof is similar to case 2. So the proof is similar to what the proof was in case 2 here. And that will actually prove Rolle's theorem. All right.